Well, thank you so much for joining us today for EBMUD's Landscape Advisory Committee General Meeting. So great to see so many of you joining us for this conversation with a special presentation on strategies to prevent urban heat in WaterWise landscapes. My name is Kristen Bowman, and I'm a Water Conservation Program Manager here at EBMUD. And just a few things to begin before we start for logistics. This presentation is being recorded, and by participating, you agree to be on a recorded webinar. We will be sending out the slides and the video and links to all the resources and events that we talk about today. So be looking for that in the next couple days. We do have everyone muted, but you can chat with each other, and I see that you're doing so great using the chat button. And then we have the Q&A for questions for the speakers. We will be looking at the chat and the Q&A throughout the presentation, and then we'll also have a period at the end of the presentation to talk to to answer some more of those Q&As. Just an overview for our presentation today. We're going to start with some announcements and then take a look at EBMUD's water supply. Then we'll head into the featured presentation. We'll end with a summary and a few trivia questions, and then our Q&A. You'll also see a survey come out just at the end, just to let us know how did it go and other things that you might be interested in. So let's begin. Just to begin with, this presentation is available. You can get CEUs from UC Master Gardeners, Quell, Rescape, and AWWA. And there are a lot of really interesting events coming up. So to save the date, February 6th, G3 and Valley Water will be offering a webinar on the new commercial landscape. I think it will be a really nice tie-in to what we talk about today. February 27th, Valley Water Landscape Summit will be hosted in San Jose, and this is also a hybrid event. And Allied Landscape will be hosting a professional training in person in Pleasanton. March 11th, EBMUD will be hosting an in-person conversation as a follow-up to today's meeting, Strategies to Prevent Urban Heat. This will take place in Oakland, and we're super lucky. Lawrence Berkeley National Labs and UC Cooperative Extension are really opening up their labs to us and saying, what do they need to study on this topic as we are looking at changing out our lawns to low water gardens. So this is a time to kind of weigh in even more deeply on this. The other plug for March 11th is we provide really good treats, and we're a jovial group. So we'll be sending out a link for that registration. Also, a little bit further down the road, Ruth Bancroft Garden Tour, April 26th. Bring Back the Natives Garden Tour, May 3rd and 4th. And then May 22nd, the California Green Building Conference. And we will have a water conservation track at that conference. So super interesting. Be sure to come out for that. Just a few updates on our Landscape Advisory Committee project committee. We are working on revising our EBMUD low water plant list and to really be more specific about plants that are going to do better on east and west of the hills, since those are distinct microclimates. So more on that to come. And the city of Alameda has a draft urban forest plan, and they're looking for community input on that. Very good document. And also the city of Oakland just passed their urban forest plan. So that might be something to look at. In terms of our landscape rebates, a few years ago, this group here really asked for some kind of ROI or payback calculator to look at how much is a lawn conversion, taking a lawn to a low water garden, how much does it cost and how much water can we save by doing that over time? And so you can literally Google lawn conversion payback calculator. It will pop up on the Stop Waste website, who helped us with this. And go ahead and try that out. We have default values, but you can also customize it. And we'll be curious how that goes for you. To help support these lawn conversions, we do have rebates as standard, which is $1 per square foot. The super, which requires sheet mulching and native plants, that's at $2 a square foot, and also changing out median strips, that's at $2 a square foot. Up to 20,000 for commercial properties, and that ends December 2026. And this is a time of year that we're actually thinking about the irrigation audits and doing repairs to our system. So to help you with that and to catch those leaks and broken heads before you turn on your system in the late spring, early summer, we have a rebate for $30 per station, up to $1,000 per account. And to kind of connect with that, we have the irrigation flow sensor, which is super handy. You connect it to the controller and then can get leak alerts in real time. Also, we know that you have site-specific concerns, and so we are offering account managers and HOA board meetings. Invite us virtually or in person. We'd love to come and talk to you about your projects and our rebates. And we're 2 years into doing our landscape design assistance program, primarily with residential properties, and getting a lot of good feedback on that. Really high-level projects, and just happy customers working with our designers. So we just launched our 3rd year. A little bit about EBMUD water supply. For our total system storage, we're at 78% full. Which is about 106% of average. Our precipitation levels are a little bit low. We've had a little dry spell, so we're at about 67% of average upcountry in the Mokelumne River watershed. And then our local reservoirs, we're at 72% of average. So I want to review this graph to the right, which is our gross water production. And it compares 2005, which is the blue line, to the last 2 years, which are the green and red line. And basically in this period right here is during our peak irrigation season, July, August, and September. And you can see in 2005, we were using 100 million gallons a day more than we are currently using. So good job, taking action with your controllers and scheduling and converting to low water landscapes. And then even during our wet season, we're quite a bit lower in terms of our water use than in 2005. And we're going to keep going with this as our population grows, and over time, we're looking to even save more water. And this is called creating a conservation culture. We're really looking to save water indoors and outdoors, drought or no drought. Over time, it becomes part of our culture. So along those lines, we do have a couple water conservation legislations that were passed, and I think most of you are familiar with the non-functional turf watering ban for commercial properties that was passed in 2023. If that's new to anyone, we're happy to meet with you to review that. We'll be sending you a link to our webinar and web page on this law. But essentially, in a nutshell, it's saying no more using potable water to irrigate decorative lawn or lawn that's not used for recreation. It has a tiered approach with government properties starting in 2027. And this is really our launching off place for our meeting today, looking at strategies to prevent urban heat, because we're looking at and we're asking the question, if we're not going to be irrigating lawn, would that have an impact on possible localized heat, and strategies to reduce that? In addition, making water conservation a way of life, that was passed in 2018, but more recently, they have solidified targets, indoor and outdoor water use targets for residential and commercial sites. And the targets over time increase the water efficiency, so become more water efficient over time. And one of the areas that they're looking at is really proper controller scheduling as a way to save water. And we're probably this spring, summer, we're going to start to really dive into that, to how do we get all layers of our industry, from our professionals down to the homeowner, really scheduling those controllers properly so we can save a lot of water. And just as a reminder, as we are moving from the lawn to regenerative landscape, there's a lot of trainings out there to train up our landscaping team and even ourselves. So Rescape California, qualified water efficient landscaper, and I noticed that Zone 7 is offering this in English and Spanish. I believe it's in March. The California Native Plant Society Landscaper Certification Program, CLCA, Irrigation Association, G3, the events that EBMUD offers, and UC Cooperative Extension is also looking to fill the gaps on landscape professional training. So they're going to offer a survey at the end of this meeting today to talk about what other resources do you need and trainings do you need to help us improve our skills and knowledge. So with that, I'd like to launch into our featured presentation on strategies to prevent urban heat with the WaterWise landscapes. We have Dr. Pouya Vahmani. He is an urban environmental scientist in the Climate and Ecosystem Sciences Division at the Lawrence Berkeley National Laboratory. Pouya's recent research includes extreme heat and energy demand in cities, municipal water conservation and heat mitigation and climate adaptation in urban areas. Pouya is going to start us off with talking about what kind of factors contribute to urban heat and then the impact of cool roofs on air temperature and irrigation. And then Dr. Joanna Solins, an environmental horticulture advisor with UC Division of Agriculture and Natural Resources. Joanna has conducted postdoctoral research on green stormwater infrastructure, urban forest composition, and the water demand of urban vegetation across California, and has contributed to projects examining residential landscaping and urban heat in Sacramento. So Joanna is going to then focus on effects of turf conversion and tree canopy on localized heat. And with that, I'm passing it on to Pouya. Thank you so much.
Yeah, thank you, Kristen, for that introduction and also for the invitation. So I'm going to jump right in. So I'm going to start my presentation by showing an animation, and we're going to see soon if that's a good idea or a really bad one. So just to set you up, so there's going to be text on this animation. Don't worry if you cannot follow the story that the text is going to say. All I want you to take out of this animation is to get a sense of and also be able to picture the tools that we use in our research and the scale at which we conduct our research. So what you're going to see is the animated animation of the simulation results using climate models, 2 different climate models that we use in our studies to look into urban heat. With that, Christine, please go ahead and start. So yeah, here you can see the simulation of a heat wave that happened in July 2018, which hit the Southwest United States particularly hard. So we're doing this using a model called E3SM, which is an air system model or a global climate model. So the point I'm trying to make here is that these models are useful as capturing large-scale phenomena, but once you zoom in over a city like Los Angeles, even as big as Los Angeles, the resolution is not high enough to give you really useful information in our cities. That's why over the past few years, we have developed a cutting-edge, really high-resolution microclimate model that can help us capture how a heat wave, for example, evolve or propagate through an urban area such as Los Angeles, and investigate the impacts of climate change or different solutions that could be implemented at city scale. So the second point I want you to take out of this is to grasp the scale at which we focus our studies, because that's going to be complemented with what Joanna is going to present after me, so which is going to have more of a local scale and more of an observation perspective into it. So what I'm going to talk about uses city scale, focuses on city scales, and uses climate models or microclimate models and tools like that. Next slide, please. So here, so I want to show you how our models see a natural land on the left and an urban land on the right. So basically, on a natural land, once the solar radiation hits the ground and the ground heats up, the energy is turned into evaporation and evapotranspiration through vegetation, or turns into sensible heat flux. That's the red arrow pointing up. So that's what you don't want. That's the heat you're going to feel during hot days, and that's what you want to minimize. But if you look at the picture on the right-hand side, you can see the story gets complicated. So not only we have evaporation and evapotranspiration from vegetation and water bodies in our cities, we also have heat coming off of the buildings and roads. Those are usually made of material that absorb more of the incoming solar radiation and generate more heat. But on top of that, we have the waste heat coming off of our transportation sector or cars and buildings because of using fossil fuels or burning energy in them, which produces waste heat, which is then dumped into the urban environment, contributing to urban heat. On top of that, we have the solar radiation hitting the buildings and bouncing off of the vertical surfaces. We call that trapping of the incoming radiation, which heats up the urban environments even more. So this is to give you a sense of what is represented in these climate models, specifically in the microclimate model that we developed specifically for urban areas, which has higher resolution. So the beauty of using these simulations or models is that you can turn on and off each of these processes to see how they impact the results, right? So you can simulate a heat wave as I showed and remove all the cars from the city, or remove all the buildings, or add vegetation, or reduce vegetation, or stop irrigation to see how much, for example, air temperature or the living experience of people will change across different neighborhoods in a city. Next, please. So using that framework, those microclimate models, one of our ongoing studies is looking at heat persistence. Heat persistence, we define it as the number of hours in a row that air temperature exceeds a threshold of 35 degrees Celsius or 95 degrees Fahrenheit. So we wanted to know, look at 4 different elements in urban areas or 4 different processes to see how they affect the heat persistence in a city, for example, Los Angeles. So we're looking at, so if you look at the chart, the plot on the right-hand side, there are 4 urban elements represented here. Built surfaces, those are roads and buildings. There's anthropogenic heating. That's basically waste heat that comes off of cars and buildings as we consume energy in those and produce waste heat, which is dumped into the urban environment. We also look at the cooling effects of vegetation and irrigation on heat persistence. And the last row shows the total change because of all these 4 urban elements. So our results shows for Los Angeles, the built surfaces and anthropogenic heating together extend the extreme heat conditions by more than 1 hour, and that's per day. So during a heat wave, you're going to have 1 extra hour of extreme heat conditions because of the buildings and cars. And what we also showed is that vegetation and irrigation together reduce the heat persistence by almost half an hour. So this shows that vegetation and irrigation can offset the warming effect of urban areas by 50%, which is very significant. So they play a significant cooling role or moderating the urban climate under extreme heat conditions specifically. Next, please. So using the same modeling framework, a few years back, we looked at specifically the climatic consequences of adopting drought-tolerant vegetation in LA. This was a response to the policy or the policies that the city was pursuing to remove lawns and replace them with drought-tolerant vegetation. This was right after the 2012 to 2016 drought in California. And so with this exercise, we wanted to kind of predict how the microclimate or heat conditions in a city of LA under the heat wave condition would change as a result of this policy if it was implemented everywhere in Los Angeles. So the plots that you're seeing here on the left-hand side, it shows the simulation results when you remove stop irrigation and replace the current vegetation with drought-tolerant one across the entire Los Angeles metropolitan area. And what our models showed was that the consequence of that would be almost 2 degrees Celsius, which is 4 degrees Fahrenheit of extra warming during the day under heat wave conditions. That is in the order of one of the worst climate change scenarios in terms of the warming effect. And another thing that was interesting is that this warming effect is not uniform. So as you can, if you look at the map that shows the Los Angeles, for example, you can see how the warming effect is heterogeneous. So some areas are going to be impacted more, some areas less. The second interesting result of this study was that we found that the nighttime temperatures are actually going to be cooler or lower as a result of this policy. And without getting too much into the details, that's a result of the greenhouse gas effect of water vapor in the atmosphere. So when you don't have irrigation, you have less moisture in the atmosphere, which during the night has a bigger impact because the boundary layer, which is the lowest atmospheric layer, is more stable, and the greenhouse gas effect is going to be higher. So that's a side note. And so the bottom line was that the daytime temperatures are going to be increased significantly, but the nighttime temperatures are going to go down if this policy is implemented significantly, and widespread. And there's a QR code on the left that would take you to this study if you want to read more and get all the details of how this study was done and the results. Next, please. So far I've talked. So as we use these tools to kind of capture heat wave dynamics in a city, and how, although I didn't talk about it, we also spend a lot of time looking at how climate change impacts the heat dynamics in a city, and also looking at different factors that contribute to extreme heat conditions. We also investigate the solution space, right? So we want to know what we can do to reduce the increasing heat risk in our cities. So here I'm showing 4 categories of what we call heat mitigation strategies that could be employed in our cities and urban areas. Just a note that these are targeting the outdoor environment in our cities, right? So as you take a walk outside, or if you work outside, we want to kind of moderate the temperatures outside our buildings using these strategies. We also do work that focus on indoor environments and how we can cool down our inside of our buildings during extreme heat conditions. There's a lot of useful information if you look up the research done by Berkeley Lab in this area. But coming back to these 4 categories, starting from the left, the first one is called surface reflectivity or albedo enhancement. Albedo is basically reflectivity of the surface. So the idea here is to use materials or coatings in cities that reflect more of the incoming sun's heat or radiation back into the space, so it doesn't warm up our urban environments as much. The second category, the second one from the left, is urban greenery and vegetation. So these are in forms of increased tree canopy or green roofs and green walls and parks. So here you can see in the picture an example of a green roof from California Academy of Science in San Francisco. So the idea here is to increase vegetation cover, which plays the role of absorbing the sun's radiation and turn it into evapotranspiration, and reducing sensible heat flux that I mentioned in a couple of slides back. So the idea is to increase evaporative cooling using vegetation. So the third one is water-based cooling strategies, which use the same concept of evaporative cooling, turning heat into evaporation, and that's how they keep the temperatures down. But the difference here is that although these are very effective measures, but their cooling effect is very local. Whether it's a pond or fountains, they will have effective or cooling but localized effects. And the last one on the right is related to urban layout and design. So this mostly concerns urban planners and architects that can use urban design to create ventilation corridors or use building orientation and spacing to allow the wind goes through among buildings and remove heat from them. So the problem during heat waves often is that the weather system stagnates and the air doesn't move as much over the city, so the heat builds up. So these ventilation corridors allows for natural ventilation that can remove heat from urban areas more easily. Next, please. So for the rest of this presentation, I want to focus on only one of these cooling strategies that I talked about, and that's cool roofs, because our research showed, and I believe this is one of the most promising solutions in front of us. And hopefully over the next few slides, I can convince you that that's could be the case, at least in California. So the idea of a cool roof is, as you can imagine here, is a bright colored rooftop. And the idea is that these type of rooftops would reflect more of the incoming solar radiation back into the space. Next, please. And as a result of that, the surface of the rooftop doesn't get as hot under the sun or during hot days. And therefore, there's going to be less convective heat coming off of your rooftop that is dumped into your neighborhood and making the neighborhood hotter. So that's the first effect, reducing air temperature around your building or around your house. Next, please. But the second effect is that there's going to be also less heat conducted through the roof inside building. And as a result of that, next, please. You wouldn't need to run your AC or HVAC system as hard during hot weather events. So when you use your AC less, you again dump less heat into urban environment. So what your AC does is basically take the heat from inside your building and throw it outside. And also, because it uses energy and often a fossil fuel, it creates waste heat, which is also dumped in the urban environment. So when you use a cool roof, you don't need to use your ACs as much. So the urban environment and the area around your house is going to be cooler as a result. Next, please. So obviously another benefit is that you're going to have cooler indoor environments, so more comfort, higher comfort level for the residents, and highest level of resilience under climate change and exacerbating urban heat problems that we're facing in our cities. Next, please. But another surprising benefit of cool roofs is that as it cools down the urban environment around the building, the vegetation and trees that are around the building are also going to benefit from these cooler temperatures, specifically during heat waves. And that results in them needing less water to survive the extreme heat conditions. So the last effect of cool roofs is that it's going to reduce water demand. So just to put this all together, so in the context of this webinar, we want to understand how outdoor irrigation impacts the microclimate and urban heat. And so we show that, so if you have less vegetation cover and less irrigation, the outdoor environment is going to be hotter. And to prevent that, you need heat mitigation strategies. But the cool thing is that as you use heat mitigation strategies, not only you reduce the outdoor temperatures, you reduce water consumption as well. Next, please. So in a study a few years back, we actually focused on that linkage between heat mitigation and water conservation. So here, this is the results of a California-wide study using microclimate models again. So we assumed a widespread implementation of cool roofs, and as a result of that, and I'm showing the results for 18 counties in this study. So the second column shows the impact of cool roofs on albedo, which is the reflectivity of the surface. So obviously that goes up. The third row shows that the air temperature in these cities and counties go down by up to 2 degrees Celsius or 4 degrees Fahrenheit. And as a result of that, our models suggest that evapotranspiration from trees also is going to go down by as much as 20%. Next, please. Another step that we did, we converted that reduction in evapotranspiration, we converted that to water use, right? So here you can see the irrigation water demand. The unit is gallons per capita per day across the 18 counties in this study. We showed that widespread implementation of cool roofs is going to reduce the irrigation water demand by up to 9% across all these counties. So the blue bars, so the bars at the bottom show the water demand, and the red on top shows how much water could be saved because of cool roofs. The QR code on the right is going to take you to that study if you want to learn more. Next, please. So I want to end on this so you'll be able to kind of picture what cool roofs look like. But the answer is there's a range, there's a variety, and there's an increasing variety as companies and the research in this field is advancing. They're coming up with new materials that don't necessarily look white, like the one on the left, that have the same effect, but have different colors and uses different materials. So the benefit of this is for the buildings to save energy or reducing cooling demand. And it also increases the roof lifespan because your rooftop doesn't get as hot during hot days and under the sun, so it's going to last longer. And the reason I'm saying this is one of the most promising solutions we have is because it could be very low cost. So it's accessible. It could be as cheap as 15 cents per square feet. So this is my last slide. I apologize that I don't have a summary slide, but let me summarize what I've talked about. Although I didn't talk about climate change, we all know climate change is making our cities hotter. And there's this concern that in California, as we're trying to conserve water and save water and change our vegetation cover in our cities, we can have a bigger extreme heat problem in our cities. And that's why it's important to find solutions that are friendly, that go along with our water conservation goals, but also reduce the heat risk in our cities. And there's a wide range of these strategies available to us. We do research into all of them. But one of the most promising solutions we have found is cool surfaces. So cool roof is one of them, but we have cool walls, cool pavements, and these are being employed right now. And we are conducting observational campaign to investigate to quantify their impacts. But they have their benefits is multidimensional and could benefit neighborhoods and the entire cities and also save water. With that, I'm gonna stop. Thank you so much.
Thank you so much, Pouya. You know, this group, we don't talk a lot about the built environment, and I love this overlap and this discovery of how much they're interrelated in what we're both trying to do together, and also making that connection with urban heat and what we're doing with our vegetation. So next, we have Joanna Solins.
Hi, thank you so much for having me, and thanks, Pouya, for that really interesting talk. So cool, literally. So I'm going to be talking about the role of trees in cooling WaterWise urban landscapes. I think it's really important to consider early on how to mitigate the potential unintended consequences of AB 1572 and other water conservation measures. So I'm really grateful to be here today to share some relevant research and management interventions. Next slide. So just to give you an overview of where this talk is going, I'm first going to talk about a couple of studies that looked at the effects of turf conversion and tree canopy on localized heat. So as Pouya said, this talk is really going to be focusing on that human experience of heat that can vary at a very small spatial scale. Then I'll share some research looking into the effects of changing landscape irrigation on the shade trees. I'll talk a little bit about the statewide climate ready trees study and my research into the cooling potential of these trees. And then finally, just a peek at some new research that will be looking at different strategies for turf conversion. Next slide. So just to make sure that everyone is on the same page, let's just quickly go over the main ways that plants provide cooling, which are shading and transpiration. So shading limits the amount of solar radiation that reaches surfaces, so it prevents those surfaces from absorbing heat and re-radiating it. Transpiration is the process in which plants take up water from the soil and then release it into the air from their leaves through tiny pores called stomata. And transpiration provides cooling because heat is required for that water to go from a liquid state in the leaf to a gaseous or vapor state in the air, the same way that sweating provides cooling for people through evaporation. And you'll often see the term, and what Pouya used was evapotranspiration. So that accounts for both transpiration and the evaporation of water from leaf surfaces and soils. And if plants don't have enough water or it gets too hot, they can close their stomata to limit transpiration and water loss. And in general, trees really outperform other types of plants for cooling in cities, largely because of their size. Their height allows them to provide a lot of shading, and they also have a large total leaf area for transpiration. However, well-irrigated turf grass also transpires a lot, so it contributes to cooling in that way. Next slide. So a big question on a lot of people's minds is how converting turf to WaterWise landscaping will affect urban heat. Given that the amount of water plants transpire contributes to cooling, there is a fear that replacing lawns with water-efficient landscaping is going to increase heat by reducing that evapotranspiration. However, tree canopy could make a difference in how this transition influences heat and also how people experience heat, especially because shading has been shown to be more important for cooling in hot arid systems like the summers that we get in a lot of California. Next slide. So I want to share two studies that looked at this question of how tree canopy affects localized heat with WaterWise landscaping versus lawn landscaping. The first was an extensive study that looked at over 250 yards in Sacramento. About half of them were WaterWise and half had turf lawns. And this study was led by Victoria Dearborn and Mary Cadenasso's lab at UC Davis, where I was a postdoc at the time. And Victoria took measurements of air temperature, relative humidity, solar radiation, and wind at several locations in each yard during the hottest part of the day. And she used this cool mini weather station that you can see in the photo. So she used these measurements to calculate thermal comfort indices, and these are designed to represent how hot it actually feels to be a person under particular conditions. So shading plays an important role in these indices by reducing solar radiation. She also recorded tree canopy cover both in the yard and in the neighborhood around the yard. Next slide. So this is our audience participation portion. Take a look at these pictures, and these represent sort of 4 different extremes of what she measured: a completely unshaded lawn, a completely unshaded WaterWise yard, a shaded lawn, and a shaded WaterWise yard. So which type of yard do you think was coolest? And this is based on the thermal comfort index. And I think hopefully we will get a poll up here in just a second. All right, and I think I will rely on Jillian and Kristen to let me know when enough folks have filled out the poll. Thanks for folks for putting it in the
Yes,
chat
I'm
too.
watching it.
Okay, thanks.
We're just giving them one more second. And okay, let me see if I can share this. Wait, oh, you guys can't see it, right?
I can't see anything.
You can't. Okay. Interesting. I'm gonna hopefully be able to share results. Here we go.
Okay. Great. Okay, so it looks like it was about 50-50 between shaded lawn and shaded WaterWise, but the shaded lawn slightly above. So good guesses.
No, yeah, no one on unshaded lawn, 0. 1 on unshaded WaterWise. And then about 50-50. Okay, so let's see what the results were.
So if you can go to the next slide. It was actually the shaded WaterWise yard. So about half of you were right there. But shaded lawns were very close. And this difference might be in part because that thermal comfort index considers the role of relative humidity. So the higher relative humidity that you might expect over a shaded lawn could actually increase that thermal comfort index. And then the hottest, which probably doesn't surprise a lot of you, is this unshaded WaterWise, where there's no vegetation on the ground and no shading. So next slide. The takeaways from this study, from what I just showed you, a big takeaway is that tree canopy is very important for improving thermal comfort in WaterWise yards. And the study also found that neighborhood scale canopy cover provided some cooling based on those thermal comfort indices. And then finally, it found that WaterWise yards that had more plants as opposed to ground covers like rocks or mulch had lower air temperatures. All right, next slide. So I also wanted to share another study that was actually led by EBMUD's very own Jolene Bertetto. And she asked a similar question, but instead of looking at a lot of different yards just one time, she took measurements at the same location, which was a courtyard in Walnut Creek, many times over the summer. And this courtyard also allowed her to compare lawn with and without shade to water efficient garden with and without shade. And again, she was looking at the pedestrian level to get that human experience of heat. And she calculated a vegetation cooling index by comparing the temperatures in those landscaped areas to temperatures in a nearby unshaded asphalt parking lot, which is shown on the right there. Next slide. So the study had a ton of interesting findings. I wanted to focus on this finding that mirrors what we found in the first study, that shaded WaterWise landscaping was actually the coolest overall and also definitely had the highest cooling efficiency if we consider the amount of cooling compared to water use. So this graph here shows the vegetation cooling index on the y-axis or the vertical axis. So again, that's the temperature compared to a sunny parking lot. And that goes from 0 on the bottom, which is the same as the asphalt. And then on the top, it goes to 3 degrees Celsius cooler than the asphalt. And then on the x-axis or the horizontal axis, we have the estimated annual water use, which increases from left to right. Thanks for showing that, Kristen. So we can see that the shaded water efficient garden, which is in that pinky color, magenta up there, thanks, had the best cooling and also used fairly little water. Whereas the water efficient garden in the sun actually used less water, and that's because it had different types of plants, but its temperature was almost exactly the same as the asphalt parking lot. And again, that we see that shading doesn't make quite as much of a difference for the lawn, and the lawn areas use much more water. And I will note that although the method that this study used to estimate water use has the shaded and sunny lawns using the same amount of water, shaded turf grass actually needs much less water than unshaded turf grass. But that doesn't mean that people necessarily irrigate it less. So overall, we get the best cooling for the amount of water used with the shaded garden. It's really nice that it actually cools the best overall. Next slide, please. So the management implications from these studies are that maintaining and increasing tree canopy is going to be very important as we transition to WaterWise landscaping if we want to mitigate the effects on urban heat, especially at these small scales. For heat mitigation, it's also helpful to include more plants in WaterWise landscaping as opposed to unplanted ground covers like rocks and mulch or paving over areas. Next slide, thanks. So we know that tree canopy is important for maintaining cooler temperatures during these transitions. However, we also need to think about how that transition is going to affect our existing shade trees. And what happens when lawns are actually just left to die instead of being replaced by new landscaping? So here we have a couple different scenarios. People may convert their lawns to WaterWise landscaping with drip irrigation, or they may simply turn off the tap and stop irrigating their yards or replace their grass with non-living ground covers like paving or mulch. So these trees these changes are going to affect the trees that were previously being watered with the lawn. Next slide, please. And this could potentially be a problem because California's current urban forests were really not planted with this type of water restriction in mind. We did a study where we looked at over 3 million trees in tree inventory statewide, and we found that most of the trees are rated as having moderate to high water requirements, with the caveat that our data set was mostly public trees in residential areas. We found that this was true for all size classes, suggesting that we have not started planting many low water tree species. And it was also true for all climate zones across the state except the Southwest Desert, which did have more low water tree species. And some of the species that were most common in at least 2 different climate zones were London plane tree, southern magnolia, and sweet gum, and all of these have moderate or high water needs. Next slide. So we conducted a field study to see how these different types of irrigation might affect one of those very common trees, the London plane tree. This is the most common street tree in Sacramento, and the mature plane trees provide really important shading in cities all across California. So we looked only at large mature street trees that were growing in planting strips between sidewalks and streets, like the ones shown on the left. And we compared trees growing in front of yards with lawn, drip irrigated vegetation, or no irrigation. And we first looked at water stress by taking water potential measurements using a pressure chamber. So this is an indication of the tree's water status. And since this was a pandemic era study, it was conducted in my neighborhood in Davis and from my front stoop. And this study was done at the end of the summer when irrigation would be most important for trees. And then we also did a visual assessment of tree canopy health on a lot more trees in both Davis and Sacramento. And we scored them on characteristics like dieback, leaf discoloration, and canopy density. And we were particularly interested in seeing what would happen in the transition to drip irrigation. Since lawn watering is actually not ideal for trees, it tends to be frequent and shallow, whereas trees really do better with frequent deep irrigation. So drip irrigation can theoretically provide more appropriate irrigation for trees, but it really depends how it's set up. It can also change the total amount of water being put into the landscape and change its distribution. And there could also be damage to trees in the process of conversion. Next slide. So we found that many street trees do appear to rely on irrigation from neighboring yards. The trees growing in front of yards with lawns were the most healthy and the least stressed on average, while the trees growing in front of unirrigated yards were the most stressed and least healthy on average. And trees in front of drip irrigated yards were intermediate, but they were more like the trees in front of lawns. So this is promising because it suggests that drip irrigation can be effective to protect trees. I should note that there was a lot of variation for all of the irrigation types, and these findings may also change over time as trees are subjected to water restrictions for longer, because the way we did the study, we couldn't really tell how long yards had been under their current irrigation status. So we're planning to assess these trees again next summer. What we can say is that increased stress leads to canopy loss, which reduces cooling, and stressed trees tend to have less dense foliage and more dieback, so they provide less shade. And then if they eventually die or are removed, they leave really large gaps in the canopy. Next slide. Another recently published study that I had nothing to do with, but really appreciated, found that trees show a legacy of past irrigation. So trees that were historically well irrigated are less tolerant of having that water taken away. And they can show signs of high stress and low productivity for years after that irrigation stops. They also had lower annual growth after their irrigation stopped than trees that had never been irrigated. So that's kind of rough news for our mature trees that make up most of our current urban tree canopy. But the better news is that trees that develop under water restriction may be better able to cope with those low water conditions. Next slide. So management implications for trees. Maintaining our current tree canopy is really important because it takes a long time for trees to grow big enough to provide a lot of shading. And to do that, we're going to need to irrigate existing trees. So deep and less frequent irrigation is best, But you also have to remember that if trees have been used to lawn watering their whole lives, they're going to have root systems that develop to take advantage of that type of watering. So it's best to transition them gradually when possible. And drip irrigation is promising for keeping trees healthy, but it really needs to be designed with tree needs in mind. I've seen tiny little circles of drip tubing right around the trunks of mature trees, and that's really not going to do them any good because the roots that take up water are closer to the edges of the canopy and beyond. So that's where the water needs to go. And in situations where there isn't a drip irrigation system, trees can still be watered properly, either using a regular garden hose or a soaker hose like the one pictured here. And then in the future, our urban forests could do well with less water. Any tree planted under water restriction is likely to be better acclimated to low water conditions, and with the caveat that all trees do need water to get established. And then we can also make a point to plant tree species and cultivars with lower water requirements. Next slide. So another thing to remember is that not all trees necessarily provide the same amount of cooling. So as we think about changing the species that we're planting in our urban forests, we need to keep that in mind. Cooling can depend on species. So trees with dense, large canopies tend to provide the most cooling, but the mix of species also matters, and diversity tends to increase cooling as well. Cooling can also depend on both context and management. So for instance, trees will transpire more if they have more water, which increases their ability to cool the air. And then high levels of paving in general can reduce transpiration and growth, which reduces cooling. Next slide. So there's some concern that shifting our urban forests to low water trees is going to reduce their cooling benefits because a lot of trees adapted to conserve water are smaller and have sparser foliage and by definition kind of transpire less. So to test this idea, I've been doing some research as part of a larger climate ready tree study, which is trialing promising species for future urban forests in 3 different California climate zones. So the trees in this study were chosen because they're not yet commonly planted in California's urban forests, but they are promising to do well in the future under future climate conditions, and particularly under water restriction. So the goal of this whole project is to introduce vetted species that will add diversity and resilience to our urban forests. So there's a total of 12 species being trialed in each climate zone across the state, a total of 3 climate zones. And they've been planted out in reference sites and in parks. And they're just now getting old enough to start thinking about their cooling potential. So we chose the 6 best performing species in the UC Davis reference site to compare with 6 common urban tree species that were planted around the same time in a planned development in Davis called the Cannery neighborhood. And the trees in the reference site hadn't been irrigated at all for 6 years when we did the study, whereas the cannery trees were on irrigation systems. And this photo shows one of the climate ready trees in the reference site. And we wanted to compare these trees to each other and also determine which characteristics were associated with effective cooling. So at the time of this study, the trees were 9 years out from planting, so clearly not mature yet, but I think it's really important to consider how much cooling we can get from trees relatively soon after they're planted. Next slide. So we took measurements at each site monthly during the summer in the heat of the afternoon, and we measured ground surface temperature under tree shade and in unshaded areas. And that was done on sidewalks in the Cannery neighborhood and then on concrete pavers under the climate ready trees. And we also measured the wet bulb globe temperature with this fun little device on the tripod, if you can see that. And that's another indicator of thermal comfort. So again, it takes into account temperature, relative humidity, solar radiation, and wind. And then we also used a light meter to measure canopy light interception, and we measured some other canopy and leaf traits that could be associated with cooling. Next slide. So we just finished data collection in September, and these results are hot off the presses, and I haven't entirely worked out the nuances of the analysis yet, but I am pretty confident in saying that trees with wide, dense canopies provided the most cooling for both the common street trees and the climate-ready trees. And I'll admit this isn't too surprising, but it is noteworthy that canopy width was overall more important than canopy height or leaf traits in predicting cooling. And interestingly, there was also no significant difference in the cooling effects on thermal comfort between these common street trees and the climate-ready trees. And so in both sites, there were some trees with these dense spreading canopies, like the Zelkova and the Canby's oak, that cooled better than the ones with smaller, sparser canopies, like the cherry plum for the common street trees and the emerald sunshine elm for the climate-ready trees. And this elm will eventually get much bigger, but at this stage, it's not really doing a fabulous job at cooling. But one thing to note is that all trees were substantially cooler than the unshaded controls. So I think the good news here is that there are trees that can grow quickly with very little water and provide shading that's just as effective as the well-irrigated urban trees that we've been planting in the past. These climate-ready trees may need some supplemental irrigation in the tougher urban sites, but they're proving pretty hardy so far. Next slide. So you may be thinking, this is great news, but how do I find low water species for my area that will provide good shade? Two great resources, you might be aware of these already, are the WUCL's database and the Select Tree database. I think they both have pros and cons, so I tend to look at both and do some additional research. The WUCL's database, so this stands for the Water Use Classification of Landscape Species, is nice because it provides a water use rating by region, since trees are typically going to need more water in hotter areas. However, it doesn't have all of the species, especially for trees, and different cultivars that you might be interested in. And it does provide a narrative description, but it doesn't really have any other search filters for trees. And just to note, it includes lots and lots and lots of other landscape plants. The Select Tree database is only for trees. It does have the disadvantage of just one water use rating for every species, so it's less precise, but it includes a really amazing number of species and cultivars, and it has a ton of information about each of them. So you can filter by a lot of different characteristics. And the site can also give you a sense of the mature canopy width and growth rate to think about the shading that it's likely to provide. And I do want to note that the water use ratings on both of these sites are primarily based on expert opinion. So, you know, I think expert opinion is extraordinarily valuable, but it's not really based on like scientific research that tells you exactly how much water the tree is using. And then in addition to these sites, a lot of cities and organizations have planting lists that can help you find appropriate trees for your particular area, but just make sure that the lists you're using have been updated recently, because sometimes lists are still in use that are really old and outdated. So finally, next slide, I just want to give a brief preview of some new turf conversion research I'm setting up with Sacramento County that I hope will provide you all with some valuable information once we have data in a couple of years. So first, we're comparing sheet mulching methods to sod cutting and a variety of different mulch, compost, and decomposed granite alternatives to see which methods for turf conversion are most effective in terms of soil characteristics and plant growth and weed and pest pressure. And then we're also going to be monitoring the growth and water status of mature landscape trees before and after we convert the turf around them to WaterWise landscaping. Next slide. So just to wrap up, trees and other plants can help mitigate heat impacts of lawn conversion. With adequate shading, WaterWise landscaping can be even cooler than lawns. And living ground cover plants also help with cooling. Remember again that the findings I've presented are at a small scale, so we really need folks like Pouya to help us figure out how it's going to impact heat at that larger scale. And I did want to note that we heard from a lot of people who are really concerned that landscaping for fire safety could increase heat because at this point, vegetation is not supposed to be planted within 5 feet of houses. So I think this is a reasonable concern, but one way to address that is to maintain well-hydrated and well-pruned trees, particularly on the south and west sides of buildings, so they can still provide shading for those areas right next to houses that are not supposed to have vegetation. And then the rest of the yard can have plantings. And where there's sort of a synergy is that well-hydrated vegetation is going to transpire more and be more fire resistant. Maintaining our tree canopy does require irrigation. So we need to consider our current tree water needs when we're doing any sort of landscape conversion and be sure to protect them during new landscaping processes. And when we're planting new trees, let's try to choose species that provide a lot of shading, but don't use quite as much water. And then finally, there are environmental justice implications for all of these changes because tree canopy and heat are already inequitably distributed in cities. There's typically more heat burden on lower income communities of color. And these landscape transitions that preserve or enhance cooling require resources for irrigation and planting. And there is some provision in the legislation to protect low-income communities, but we need to be sensitive to different abilities to implement these solutions. And with that, thank you so much.
Thank you so much, Joanna, for sharing all that research that has been conducted in en route and just really highlighting the fact that, you know, we get a law like AB 1572, which says stop watering turf, but then how do we move through that in a really thoughtful way so we continue to improve our outdoor environments? And I think you came up with some really excellent solutions on that. So, did you want to talk about this for a minute?
Oh, yeah, sure. So as Kristen mentioned earlier, it's our job at UC Cooperative Extension to
Oops.
extend information to landscape professionals. And we would really like to know what would be most valuable to you. So if you are a landscape professional and you have not yet taken our survey, we'd be super, super grateful if you would give us your opinions. So thank you.
We'll send that link out also with the email, follow-up email. Did you want to say?
Oh, this is just, everyone to thank who contributed to these studies.
Yes, super important. And so just as a summary, our state water conservation policies outline an increase of indoor and outdoor water use efficiency over time. The ban on irrigating commercial non-functional turf with potable water has a tiered timeline. It starts with municipal properties in 2027. And based on recent studies, that Pouya and Joanna presented today, replacing lawns with low water plants, ground covers, and a diversity of trees helps to reduce localized heat. Cool roofs have shown to reduce irrigation demand of the surrounding landscape. And it's recommended to put trees on separate hydrozones from the other part of your landscape, and also to match the irrigation requirements for established trees and new trees. They're different. Established trees, you may want to take a slower approach to weaning off the water because they're used to a lot of water. Though new trees may be more adapted to being more water efficient. And there's a lot of trainings available. Take advantage of them for your team or for yourself. There's also talk of creating a streamlined pathway for the C27 landscaper contractor's license. And so we'll keep you up to date on that. And EBMUD has a lot of rebates and resources to help you with all these landscape changes. And just a quick trivia. You're welcome to put this in the chat. What color are some cool roofs? Seeing a couple answers there. Yeah, there we go. Exactly. We were listening. What city published a draft urban forest plan, which is available for public comment? Does anyone remember that? Alameda. That's right. Jerry got that. And then lastly, can you name one organization that offers a landscape training? CLCA, Quell, very good. You guys, yeah. Rescape, there we go. Yes. Okay, and now I'm gonna head over to the Q&A box, and I see the chat was super busy, but I'm thinking that was primarily you talking amongst yourselves. So let's see. Yes, we will put a link to the key. Yeah, okay. A wildfire country has so many of our big. So this is a wildfire question. In wildfire country, as so many of our big trees are cut down, what is the impact of replacing dangerous, often poor-sighted big trees with smaller, prominently deciduous trees? Any suggestions, strategies on that? I'm going to send that to you, Joanna. Can you see the question? I don't know if you can see.
I probably could find it, but the chat is a little
That's
overwhelmed.
okay.
Oh, it's
Yeah,
the
it's in the
Q&A,
Q&A.
right?
Yeah.
Okay. Yeah. I think, well, there will be heat impacts of taking those trees out, but you know, it may be worth it if they really are dangerous. And you know, if the whole area burns up, it's going to end up with no trees and hotter than if you protect what's there. So I think again, making sure that you're planting trees that are going to do all right with the water regime that you have in that particular area. And for houses in particular, focusing on planting to the south and the west to make sure that houses are shaded, I think would make a difference. I'm sorry I don't have like a magic bullet answer for that.
It's tricky, you know, it's just a tricky overlap with trying to shade and also prevent forest fire, you know, these fires, but kind of what you said, Joanna, keeping things well hydrated, doing the right type of pruning, following the local fire codes for those specific locations. And then if there's a zone zero that you need to comply to, doing that. But there isn't a perfect answer, but being cognizant of some of these best practices, I think for right now is what we can do. How do green roof either intensive or extensive, and who do green roof? I don't know. Either intensive or extensive in Santa Clara area. I'm looking for experienced contractor for extensive roof. I don't know, Pouya. Not sure about that one. Maybe,
I think they're asking to find contractors that can help them install green
yeah,
roofs.
yes. Do you have any kind of website or anything about green roofs?
Not really for contractors, no.
No,
Sorry,
yeah, but it's a
sorry.
really good question because it's such a good solution, right?
Mhm.
What strategies will be used to reduce the increased heat with, yeah, with the loss of trees?
Yeah, I mean, the four categories of heat mitigation strategies that I showed, all of them could be, I mean, could be leveraged. Specifically, I think reflective materials or cool materials could be very promising in California.
There's a lot of questions about like removing invasive trees. Will heating impacts be significant? Trees, rock? Will heating impacts be significant if a tree has a rock mulch under the canopy?
Uh, So, I mean, maybe it's a good idea to point out, I answered a lot of questions. So if folks go to the answered
Oh,
questions, that
uh-huh.
could be useful. These are the ones that are left. So
Mm-hmm.
I addressed this, but so there was a lot of questions about the study I shared in Los Angeles that removed lawns and replaced them with a low density vegetation and no irrigation. The
Mm-hmm.
questions were what if they're replaced by rocks or gravel? That's a good question.
Mm-hmm.
That in that study we didn't address that, but from previous studies and on our understandings of the physics, if you add rocks and gravel that have high heat capacity and conductivity, they will have same effect as concrete and asphalt. They absorb a lot of energy and they release it throughout the day and night and increase heat persistency. So it does matter what you replace the turf with, and all rocks, maybe it's not a good idea as it exacerbates urban heat island effect. But if they're under tree, their effect could be reduced because they won't be exposed to much sun, so they won't warm up as much.
Joanna, did you have anything to add to that? You were saying that um It's better to plant than use too many rocks or just mulch in a garden.
Well, no, I think what Pouya said is exactly right, that as long as it's shaded, it's not going to have the same heat impacts, but you also won't get the transpiration from plants.
Yeah.
So
This is a good question. How gradually is good to transition trees to drip? What should I tell our customers doing these conversions who want to, they want something specific. So they've taken out their lawn and they're trying to preserve their existing trees. How gradually? Can you give a
that's a
ballpark?
great question. I
Yeah.
imagine there's actually probably some people in the audience here who have a better sense of that. I would I mean, different lawns also have different lawn watering regimes. So thinking about what the tree was used to and trying to ensure that the amount of water doesn't change at first, but you can start decreasing the frequency and increasing the depth that that water is going to go. I don't know, maybe Jesse has a good idea about this.
I was just going to say that one of the people in the audience is Igor Lachin, who's the Bay Area Urban Forestry Advisor. And I know that he's got some rules of thumb about transitioning trees out of lawns and into drip irrigation, lawn irrigation into drip irrigation. Maybe he can throw those rules of thumb into the chat.
Igor will be following up with you because now you're known, and that
Yeah.
sounds like some good information to know for all of our lawn conversion programs. Are diseases like emerald ash borer or Dutch elm disease considered for climate appropriate trees?
Um, yes, in general. So at least for the species that were chosen for the climate ready trees study, they did consider pest susceptibility. So the elm that was part of that study is Dutch elm disease resistant. And there are no ashes in the study. I think that local planting lists are often still catching up with those threats.
And then kind of a follow-up, do you have a list of climate ready trees that you used in your study?
Yes, there is a website, and I can pop that in the chat or yeah.
This, okay, Saxon Holt, are there studies about the quality of captured stormwater in bioswales and curb cuts as to how they affect street trees, e.g. petroleum contaminants and microplastics? I think they're worried about the quality of the water that's captured in the bioswales and how it affects street trees. Is that a research to be continued?
I would say that that is an area of research that I am not current on personally. So I will have to pump that, but it is a great question, and I could follow up later.
Yes, maybe that's
Unless you
part
know,
of our
Pouya.
in-person event. So we are right at 3:15, and I know there's still a lot more really good questions, and thank you for your thoughts today on this important topic. We are going to host on March 11th another a deeper dive on this conversation in areas that we can prioritize for Berkeley Labs and UC Cooperative Extension to continue their research on this topic. So we hope you join us for that. And for today, thank you so much. Be looking out for our follow-up email with links to all these resources. Thank you so much for your input.